Well, hello, and it's time for our last topic in this set of 2D motion, and we're talking about relative velocity. But before we go any further, I do have a joke for today. Where does bad light go? Well, it must go in a prism. All right, moving on into relative velocity. When we start talking velocities, the key thing is looking at, again, a frame of reference. And I think I've talked about frame of reference in a previous video, but I just wanted to, again, talk about it in terms of these relative velocities, because it works for not only velocity, but it also works for acceleration because they're both vector quantities. So here I got a couple of pictures, and I want to just talk a little bit about the pictures. When we were in 1D motion, we did look at things like the two cars that we can see here, and if they're heading towards each other with velocities, it would appear that from the perspective of the police officer would be his velocity plus his velocity. So you actually see relative to it, it looks like the car is going a lot faster. But if I'm from the standpoint of, say, the observer on the side, I'm going to look at the two cars and I'll see them in their own each individual velocities. Anytime we look at this, we can kind of get a same feel for this on a car. Because if you're on the interstate traveling along at 65 miles per hour and then another car comes zipping by you at, say, 85 miles per hour, to you as the observer inside the car, you're only seeing the car traveling at 20 miles per hour, which is the difference between the two. So again, it depends upon where as we are, either the observer, either in the moving vehicle or not. The same sense, we look at say, acceleration in an elevator. Here we have an elevator that's going up. Well, we automatically have the effects of gravity of 9.8 meters per second squared acting upon us when we're in that elevator. But the elevator decides to all of a sudden start to accelerate up. We get the effect of having more than 9.8 meters per second squared acting upon us. And that's how we feel like we're getting pulled into the elevator, how we feel like the effects of G-forces. And then if we look at the elevator going downward, if it's accelerating downward, all of a sudden the accelerations are acting together and we feel more like a weightless feeling because we're actually getting effects of less than 9.8 meters per second squared because of the direction in which the elevator is going relative to the normal acceleration due to gravity. The last picture that I do have here is a picture of our bomber plane dropping the bombs, and I know we've seen probably some of these types of problems or a problem like this in class or on an assignment where we have an airplane and it's dropping the bomb, and then the bomb actually, you'll notice that the bombs all stay kind of in a line with the plane because, again, they have a starting velocity that's in the x direction that's the same as the plane, and so they actually fall right on top of the target, and the plane's actually going to be right on top of the target at the same time. So again, it looks at relative to where we're looking, and so we have to kind of judge those types of things. Now, when we read into some of the things that we're going to see on a problem set, we look at say, two velocities that are not acting in the same direction, and that's kind of where we see our problem set and what we're going to be working on tomorrow. So here I have like a typical problem where I have, say, a river current, or it could be an air current, or a wind or something like that that's going to force me to move in a certain direction. And so if my boat's on this side here, so here's my boat and my boat river, and it has a velocity this way, all of a sudden the river's current's going to drag it across, and so we end up with a resulting velocity to the observer that would be standing on the other side. Okay, and so you can see that we're always going to be traveling relative to maybe another velocity. So this is kind of how we set up these problems. These are our two velocity type problems. I'm going to walk through an example then with this one. So here's my example problem in which we have a river flow, and I'm going to see if I can pause this right now and take camera off. Okay, I can't pause it or I can't take the camera off after I've started this one, and then I think I've got enough time that I'm going to try to do this example problem with the content on it. So I'm going to try to make sure I write without going over the camera, so we'll see if I can manage that. Here we have a river that flows due east at 1.50 meters per second, and the boat crosses the river constant from the south shore to the north shore, but maintain a constant velocity of 10 meters per second due north relative to the water. And so what we want to see is what is the velocity of the boat as viewed by the observer on the shoreline. Now again, problem solving technique number one, anytime I do one of these, I want to draw a picture. So I'm going to draw my little picture here. Here's my north shore, okay, and then here's my boat that's in the water that needs to go across. It'll have a velocity of 10 meters per second, and then the river's flowing due east. So in other words, the river is flowing due east at 1.5 per second. Okay, now I didn't draw my arrows very proportionately. This arrow should be considerably smaller than that arrow because it is a smaller velocity. But we've got our observer over here on the shoreline, and we say, okay, well, where is it that what is the observer going to notice? And if I just kind of switch my colors here once to see what my resultant looks like, well, my resultant is going to be something like this, and so there's going to be an angle associated with that. So let's go ahead, and now we've got our little picture done. We've set it up. Oh, there's one other piece of information, which is the 325 meters. That's how wide the river is. Okay. So we kind of have two questions here. What is the velocity of the boat, and how far downstream is the boat when it reaches the shore? Okay, so I'm going to set this problem up. It looks like a nice little triangle problem. So I look at my triangle, and I'm going to say I'm going to have a little triangle that look like this. There's my right angle. This is going to be 1.5 meters per second. This is going to be 10 meters per second. And so I'm looking for the hypotenuse side, and we call that, of course, C if we're using Pythagorean's theorem. So C is equal to the square root of A squared plus B squared, and then we're going to take the square root of it. And so when I actually go through and figure this out, it ends up coming out to be 10.1 meters per second. Now again, that's only the magnitude part of it. So now I also have to have the direction component to this to make this a good vector, because it is a velocity that I'm looking for. So I need to now find the theta, and so to find the theta, it's going to be the theta is equal to the tangent inverse of my side opposite divided by my side adjacent. And then when I punch the numbers on this one and get my answer, I find out that I have a degree of 8.5 degrees, and I'm going to say this is going to be down the stream, or with the flow, or with the current. Okay, so again, what I'm implying is that the flow of the river is going this direction, okay, which means that if the flow of the river is going that direction, I'm downstream, I'm following the flow of the current. All right, now that takes care of my first answer. So there's my magnitude, there's my direction. Okay, the next thing I want to do is find out how far down the stream, okay, I end up. Okay, so now again, I'm going to base this off of that 325 meters. So I'm actually looking at like almost similar triangles. So there's going to be this triangle that has the length, or the one side of 325 meters, and then there's my velocity triangle, which had 10 meters. And so it's all going to be proportional, or I could set this up as a set of proportions. And so I'm going to do that. I'm going to take the 1.5 meters per second over the 10 meters per second. That's my one triangle. My similar triangle then would be x meters over 325 meters. And then I'm just going to cross multiply and solve for x. And this is how I then get an answer for x to be 48.8 meters, again, downstream. So that's my distance that I am downstream on this problem. Okay. Now, that gives us an example problem to look at. Again, this is our last topic. I don't think I had any web resources for this one, but what I am going to do is I wanted to go back and show you the reading, and the reading comes from the physics classroom. Now, if you haven't had a chance to, at this point in time, go back and look at what the physics classroom is, it's a source that's almost like an interactive textbook. And so it's a very good one, and the page that I pulled up for you on this one is called Relative Velocities and Riverboat Problems. So it's kind of goes through the content of what we're talking about, and so it takes you through 1D motion versus the 2D motion. And so here we have our airplane, and the wind velocity is actually coming at an angle, and so they talk about how we're using Pythagorean's theorem to solve that. And we can go through, and there's a couple of them showing the river boats and how we can do the same type of thing. There's example problems that you can see. And the nice thing is that when you get down here to the bottom, you can actually do some of these little check your understanding, and this would be a good thing for you to do, so to see if you actually are understanding what we're talking about. And that's why I like this this website in particular as a web source, because it's like a textbook, only that it's actually got those questions that you can test yourself to see if you know what's going on. And so if we have a plane that can travel with a speed of 80 miles per hour with respect to the air, determine the resultant velocity of the plane. If it encounters a headwind, okay, so if we encounter a headwind, that means that the wind is coming directly at us, and so the speed of the plane would be, you know, only 70 miles per hour. But if we have a tailwind, all of a sudden it's pushing us, and so then we'd end up at 90 miles per hour. But then if we have the crosswinds, that's where we actually go through. And the nice thing is once we try these, we can actually see what our answers would be, and so it talks about how we would go through and do these using the things that they learned or show on this page. So that is again the end of our topics for 2D motion. So we do have relative velocities and projectiles. We are tying in a lot of work with vectors, and so now at this point we're going to be ready to take again one of our nice little tests to make sure we know what we're doing, and the test should be made up again of multiple choice questions with this. So hope you enjoyed, and if you have questions, make sure you post to the doc, and we will see you tomorrow.